Hi, I'm Jeff Duffy. I'm a senior technical advocate for DynamoDB.
I'm Lee Hannigan. I'm a DynamoDB specialist SA at AWS.
And we're going to talk to you today about how to build some modern applications with DynamoDB and ElastiCache for Redis. And today what we're going to cover is a use case that's going to help guide our application architecture. We're going to talk about the choices that we're going to make for the data architecture, for the user interface, and the application itself. We're going to talk a little bit about the alternatives to that architecture that we selected and why, if our requirements were different, we might choose different services. We're going to give you a demo of the application itself, just to give you a sense of what it's supposed to do. And then we're going to do a detailed walkthrough of our implementation, including, our CloudFormation template and some of the code that we're going to use to implement it. And we're going to save a little time at the end for Q&A. So our use case today is that we've been engaged by a startup who wants to get into the rental business, and they want to build a rental property system that stores and queries data for rental properties. And they want to let their agents update and change data about rental properties when they need to, but they also want to let their customers search for rental properties that are around them to identify, where the options are, and then dig deeper to understand, the details of those properties. So here are some characteristics about this customer's workload that are going to help us choose our architecture. So they're really concerned about things being cost efficient during periods of low utilization. They're a startup, they don't have a lot of customers yet. And even once the traffic increases, property updates tend to be pretty infrequent. So they want to make sure they're not paying for something they're not using. They need reads to be low latency, but also high performance, because that property search traffic tends to be extremely bursty. You're going to get people who mostly tend to look for rental properties on the weekends or after work, and that traffic's going to spike. Our system needs to be able to handle that. They want to be able to do fast geospatial searches of that property data. They want their customers to be able to find properties around them within a given area. It's very, of course, important where the locations are, and so that's got to be easy and performant. And then finally, they need this to scale very easily. So they have some aggressive expansion plans for their coverage areas. And, in the event that they get lucky and their system goes viral, they want to make sure that it's very easy for the system to scale up to handle the additional traffic. So for their system of record, we're going to choose Amazon DynamoDB because DynamoDB is a fast, flexible NoSQL database. It offers a pricing mode, capacity mode called on demand that lets you just pay for what you use, which means it's going to be extremely cost efficient during those periods of low utilization. But on demand mode also allows you to just use more of the database, and it scales very easily to handle that increased scale. So it's going to fit those customer needs very, very well. Of course, DynamoDB is going to offer all of the other features that this customer will want in the future, maybe transactions, of course, all the security features like encryption and rest of transit. It's very performant, single-digit millisecond latency. And then when they want to do that aggressive expansion in the future and maybe expand to other countries, global replication is built into the system. We're also going to add Amazon ElastiCache for Redis as an in-memory data store in order to serve the geospatial query and the low latency read requirements for the application. And so ElastiCache is a managed cache system. We're going to today be talking about ElastiCache for Redis, which is compatible with open source Redis and offers extremely low sub-millisecond latency for data retrieval, and also is very easy to scale as well. And so we're going to meet that low latency, high performance read requirement. We're going to support those geospatial queries that we need, and we're going to support the scale requirements for this customer. So our data architecture for this application is going to look like this. We're going to use Amazon DynamoDB as the system of record, and we're going to use Amazon ElastiCache for Redis as our read cache and our geospatial search engine. So how are we going to get data from DynamoDB to Redis? Well, the answer is that we're going to use a Lambda function. So DynamoDB has a facility built into it called streams that allows you to do change data capture. Anytime something is added or changed to DynamoDB, it creates an entry in a stream, and we can create an AWS Lambda function that will be triggered to then go update ElastiCache for Redis and reflect that data change there, so we can use it for those geospatial searches or those point reads. Now, we could choose some alternatives to this if we needed to. So for instance, for a system of record, we could use a relational database like Amazon RDS or Aurora. So why didn't we choose that in this example? Well, because this customer was really concerned about the database being inexpensive if they weren't using it all in the early days. RDS and Aurora are both instance-based systems, and so they won't quite meet that requirement as well as DynamoDB. So Dynamo offers its own read cache system called DynamoDB Accelerator DAX. So why didn't we choose that over Redis? And the answer is because we need that geospatial search facility, which DAX doesn't support. Also, we could have chosen to use Amazon MemoryDB for Redis, which is a kind of a persistent version of Redis, a managed service as well. But again, so MemoryDB isn't quite as on demand and pay per use as DynamoDB is to meet that particular customer need. Finally, for the geospatial search requirements, we could have used something like Amazon DocumentDB with MongoDB compatibility. It actually has much more robust geospatial search functions, but again, not quite serving the on-demand need. And that's going to be true as well for the Amazon OpenSearch service. And finally, DynamoDB has a number of geospatial libraries for a bunch of different languages out there that you can use for DynamoDB itself in order to serve geospatial queries. But a lot of those libraries haven't been maintained in some time, and a lot of customers are not terribly comfortable with using something that's not in active maintenance. So when we look at the user interface architecture for our property search, we figured out how we're going to store our data. We're going to use Dynamo for the system of record and Redis for our geospatial searching and read cache. How do we get the data to the customer and to their user interface? And so starting at the left, we're going to have a simple website in today's example. It's a JavaScript client. And it's going to call APIs as you do with modern architectures in order to store and retrieve data. And we're going to use Amazon API Gateway as the interface for that API. An API Gateway is a managed service that lets you front data or systems. In this case, we're going to use AWS Lambda as the thing that it fronts in order to provide security and functionality for APIs. And then API Gateway will communicate and sort of proxy that request through to AWS Lambda functions, which themselves are going to do the required amount of storing or retrieving of data for the customer and returning in the API response. So here's what our complete architecture looks like. And while this is a pretty complicated diagram, we're going to take it in chunks to sort of talk through the individual details of the system we'll go through today. So up top in the green, you're going to see the property update flow. And starting at the left under web client, we have an agent who wants to update a property and maybe change the price or maybe add a new property to the system. So they're going to call that property status API up top. They're going to call through API Gateway, which will trigger a Lambda function that's going to update properties. And that Lambda function will write the changes to our DynamoDB table. On the right, you're going to see in that white box our cache population flow. And so what happens is that every time a change gets made to our DynamoDB table, it creates an update event in a Dynamo stream. And that stream will trigger a Lambda function who will go and populate the cache in ElastiCache for Redis. So if a update or a change gets made to a property in the DynamoDB table, this will then flow that change and populate the change in ElastiCache for Redis. You'll see above the Redis cluster something called Secrets Manager that I haven't talked about before. One of the things we're going to show you today is that newer versions of Redis and ElastiCache for Redis support role-based access control. So it used to be you just kind of used a shared key, and that was the extent of security in Redis. Well, today we support more sophisticated RBAC, and so we're going to make use of that. And one of the things we're going to need to do is to securely store the credentials used by the Lambda functions to access Redis. And we're going to do that using Secrets Manager, which can securely store data that Lambda can retrieve and use to access the system. So finally, on the bottom left in the orange, we're going to see the property query flow. And this is the flow for users who want to be able to search for properties around them or get information about a specific property. And so their client is going to call this API Gateway endpoint for the property search. That again is going to trigger a Lambda function, which is going to go and retrieve the credentials it needs to talk to ElastiCache for Redis. And then that function is going to query the Redis cluster, get the information it needs, and return it back through the API to the customer. So one of the things we want to call out is that the network architecture when you're using Lambda is something you need to think about a little bit. So services like Amazon API Gateway, AWS Lambda, DynamoDB, and even Secrets Manager don't need to operate inside a VPC in order to work, right? They can operate outside and use public APIs to communicate. But Amazon ElastiCache needs to run in a VPC. And so we're going to need to configure our system in such a way that our Lambda functions can both talk to ElastiCache and to DynamoDB and Secrets Manager. So when you want to use a Lambda function to talk to a VPC, you have to configure it for VPC access, which creates an elastic network interface. And that means that all the traffic is going to flow through the VPC. That's great, very easy to talk to our ElastiCache cluster nodes, but how do we talk to DynamoDB and Secrets Manager then? The answer is VPC endpoints, which are endpoints that you can configure in your VPC and set them up to allow Lambda, as you can see, to communicate through those endpoints to the services that it needs to talk to. And we're going to show you in more detail how to configure this later. So high level, it's important for us to kind of talk for a second about the schemas in DynamoDB and Redis, so you're going to understand how they relate. If you're not familiar with DynamoDB, tables contain items, which are kind of like rows in a relational database. And when you query data in DynamoDB, when you do gets and fetches, you have to provide the primary key, which has to be unique for every item. And so you have to provide this at least what's called a partition key, which is what we use to sort of divide your data behind the scenes to make Dynamo perform it. And then you can provide what's called an optional sort key. So for today's design, our partition key is going to be the agency ID of the agency updating the property and the ID of the agent who is updating the property. We're going to join them with the pound sign. So you can see an example below there where those two numbers are. And then we're also going to have a sort key, which is going to include some locality information like our city and our address, also put together with the pound sign as well. And the combination of these two things will form our primary key, which will be unique for every item or property that we put in DynamoDB. And this is what that schema will look like if we put it in DynamoJSON. One of the things that we need to point out early to understand, so DynamoDB, while it's sort of a key value style access pattern for a database, it supports what are called non-scalar values. What that means is like you can have an attribute in your item that actually has a complex thing like a list or a map underneath it. So you can get some pretty complex schema designs, but Redis doesn't support that. Redis is more of a true key value store where every value has to be just one thing. We can't go multiple levels. And so knowing that, we have designed today our schema in DynamoDB to accommodate it. If you hadn't and you wanted to use this system, that would be perfectly fine. You just have to do some extra work in your Lambda functions to sort of flatten your Dynamo schema. So then when we take a look at what it looks like to store this data in Redis. So Redis is more of a simple key value store. And so what we're going to need to think about is that every property and all the details for that property are going to have a key associated that we need to store in Redis. And that key needs to be unique. But the good news is we already have a unique key. It's the primary key for DynamoDB, that partition key and sort key put together, in this case, with another pound sign. So you can see an example here of where we've created a property key by combining those. That's how we're going to store the details of a property in Redis. And below is just an example command that you can use. This is Python to store that data in Redis. We're going to set it with that key and then map all the details to it for the property, like the price and the location and things like that. We're also going to, though, use Redis not just to store this data as a cache, but to index for geospatial queries. So Redis offers this by calling a command called geoadd. And what we need to do then is to give it a key and then the property longitude and latitude. So that'll let us then do a two-step process of storing the key in the cache and then adding it to the geospatial index for customer use. Then when we want to get the data out of Redis, we're going to do geospatial searches. And we simply do that by saying, hey, that first part, the properties, that's just the key name that we're picking for a geospatial index, could be anything. And then we're going to pass a latitude, a longitude, a radius of distance, and then a couple other options that say, hey, I want to understand how far this property was from my search center and what the coordinates of it are. And you'll see an example there that if you call Redis for this, you're going to get back a list of lists, each of which has the data for a particular property, its location, its distance from center, and so forth. One of the things we'll point out that we did in this design was to make sure we had enough data encoded in the property key that we didn't immediately have to go back to Redis again to get more details to display the property in the UI, because round tripping for every property, if there are a lot of them, would generate a lot of additional traffic. Instead, we intentionally encoded enough bits in here that we could show the properties. And then if you need to dive down and get all the details for the property, we can do what we show at the bottom here, which is to retrieve the details by that property key. We call Redis and say hgetall, which hash get all, get me all the details for this hash, and it'll return all of those details to you so you can populate them in your UI. So we're going to have all of the code and samples that we're showing you today in a GitHub repo that's available to you. We're going to post a link for you in the chat as well. But you can find it at github.com/AWS samples/DynamoDB ElastiCache Geospatial Workshop. And so we have to make a couple comments about this. First, this is not production ready code. It's intended to be a sort of teaching device. So there's lots of comments, lots of logs in there and so forth to help you understand how the system works if you want to try it yourself. The other thing that we'll mention is that it's not 100% plug and play because of dependencies that the code needs and some of the packaging that needs to happen for Lambda. We've given you instructions in the README file for things that you'll need to do in order to get this deployed, but it should be pretty simple and not more than a 5 or 10 minute job to get up and running.
So I'm just going to take you through the application and just show you how we interact with Redis and how we get the locations for each of the properties. So what we use is the center of this map as our latitude and longitude to send to Redis. So every time we move around the map, we get a new center, which sends our request to Redis. So what happens every time we move, we send the locations to the API gateway. That then sends the request onto a Lambda function, which does the geo search on Redis, returning us a list of properties. It returns us only the latitude and longitude of the property, as well as the property key. So you can see in these little boxes at the bottom that we parse parts of the key just to make it the application look a little bit more complete. When we click on an individual property, we do another request to Redis. So let's say we click on this property. That does another request to Redis with the key that we got returned in the previous request. So that does API gateway again to Lambda function, again to Redis and back, and that gives us all the details for that exact property. From there, we can edit the property. We can change anything, which again populates the cache. So let's imagine we want to change the price of this property to $1,000. So we click on edit property. We scroll down to the price. We change that down to $1,000, and we hit save changes. So what that does in the back end is it goes again to API gateway. It updates it goes to a Lambda function. That Lambda function updates our DynamoDB table. Our DynamoDB table then exposes that change in the change data capture streams. And from streams it goes again to our Lambda function, which populates our cache. So if we were to go back to that property now, we can see that the price has been updated to $1,000 per month. And that is all done through API gateway into our Lambda functions and updates whatever is needed. So to understand this a little bit better, we're going to go through the CloudFormation template associated with all our resources. We'll go through piece by piece so that you understand exactly what's going on in the back end. So now we're going to go through our CloudFormation template where we initiate all of our resources. Everything's handled by a single stack. So we're just going to go through it from top to bottom. First of all, we create our VPC. Our VPC then is used to containerize all of our subnets and our resources. So this is one subnet. It gives us the available IPs from 0 to 63. And we assign that to a single AZ. So for high availability, we created 3 subnets. Here you can see subnet 2 and subnet 3. So we have 3 subnets for high availability for both our Lambda function and for our Redis cluster. And they're created across 3 availability zones. If you see here, this is availability zone 2, which is our 3rd availability zone for that region. Then we create a route table, and this just allows our VPC to interact with our subnets and where the flow of the requests go. Then we associate each of our subnets to the route table, and that goes through here for the 3 subnets. Then we allow a security group. So the security group is used to access anything that's inside the VPC, be it the Redis cluster or the Lambda functions. And it's a self-referring security group, which means it basically allows access from itself. So if you assign that, anything you assign this security group to, it'll allow access from anything else that is also assigned that same security group. This is where we define our security group ingress rule. So this is allowing TCP traffic from port 0 to port 65,535. Then we declare our VPC endpoints, as Jeff previously mentioned, to interact with some services which are outside our VPC. We need a VPC endpoint to do so. This prevents us from having to try and go across the public internet. So here we have our secrets manager endpoint, which holds our secrets, which we use for access to our Redis cluster. Here we have our DynamoDB VPC endpoint. This allows access to our DynamoDB table to store our record of state. And then we have our DynamoDB table. So as the requirements, as Jeff said in the beginning, our requirements was that our DynamoDB table or whichever data store that we use handles periods of low traffic well. And for that reason, we used a billing mode, pay per request, which is a DynamoDB on-demand mode. You pay for every time you write or read. If you don't write or read, you don't pay. So that suits our use case where the customer is making very infrequent writes and sometimes long periods of no activity, which the customer will not need to pay for. That then we initiate our Lambda functions. So the first function we come across here is the function that we use to update our Lambda function or update our DynamoDB table. Sorry. So we just give it a name. You have to define your Lambda function handler for each of the Lambda functions. You assign it a role, so it has the necessary permissions to interact, in this case, with the DynamoDB table. You assign it a security group ID, and you tell it then what subnets. So to be highly available, we give it 2 subnets. Here's where we say our code, where we store our code. So we zip up our code because our code uses some external packages such as Redis Pi. We package those up and we store them in S3, and then we define our S3. So this is my bucket for the workshop, and this is the path to the key of the zipped up Lambda function that we keep there. Then we have our Lambda function runtime, our timeout, our tracing config, and our environment variables. So from here, we grab the environment variable, which is table name, so that the Lambda function knows which table to update when we send requests. This is our permissions. So this is allowing API gateway to invoke. So every time we hit the API gateway, we want to pass the request to this Lambda function. So this is allowing the API gateway permission to execute that Lambda function. And that's the same for all 3 of our Lambda functions. This Lambda function then is a little bit different, that it consumes from the stream and not from API gateway. So what it is, it's handling any changes that are made on the DynamoDB table. You'll see that it'll have a little extra configuration at the end. So again, we have a depends on, which means that the IAM role and the replication group must be created before we can create this Lambda function. We give it a security group again. Again, we give it 2 subnets. The code comes from S3 as before. Same settings here, but this time for environment variables, we have the endpoint for our Redis cluster. We have the secret ARN for our ElastiCache secret, and then we have just a string for our geo index key. And then we assign the event source mapping. So a Lambda event source mapping is how we map the DynamoDB stream to our Lambda function. We're taking it in batches of 10, which is probably a little bit unnecessary since the number of writes to our DynamoDB table are going to be low. Batch size could probably be 1 for this use case, so that it's as close to real time as possible. Enabled is true. So if you emit enabled, it's default false, which means that for changes in your DynamoDB table, the Lambda function won't actually be invoked. And then we're saying that this is the stream which we want to tie this event source map into, belonging to our DynamoDB table. And then the function name, the number of retries, which is 5. This again also defaults to -1, which means that your Lambda will continue to retry for the period of that item remains in DynamoDB stream, which is 24 hours. You wouldn't want something retrying for 24 hours, so we give it a retry attempt of 5. If you were to do this, in a more you'd want to actually have a DL queue there. So after the 5 attempts, you would want to store that item which you can't persist in a DL queue, which is a dead letter queue, and then maybe have some other process which is retrieving from the DL queue, and you can further action that, maybe store it on S3 for further insight. Then we have our third Lambda function, which is our query function that allows us our geospatial queries. Much the same as before, we just assign it the role, the Lambda function handler, security group, our 2 subnets, codes coming from S3, and the environment variables are the same as the other one. So that's pretty much the same. Again, this one's been invoked from API Gateway, so we allow API Gateway to invoke that. Then we assign a role to each of our Lambda functions. So we just, for the sake of this workshop, we just assigned a single role. We allowed that role administrator access, which you definitely wouldn't do in the real world. So you would want to make sure that this access is only allowed things that you need, such as update the DynamoDB table, search on the Redis cluster, access your secrets in Secret Manager, those sort of things. And then we have a log group. So the log group then is just somewhere where we're going to log our all of our, anything that happens in the Lambda function that we log out, we want to log that in CloudWatch logs. That brings us then to API Gateway. So this is where we define our APIs. So first of all, we create a REST API, we give it a name and a description. It's pretty straightforward. Then we create a deployment. So each of your APIs is associated with a deployment. So we just give the deployment a stage name. Everything else is pretty standard. To access API Gateway, there's certain ways you can access. You can use Cognito. You can use an IAM role attached to perhaps an EC2 instance. But for our use case, because we're accessing from a local machine, we use an API key. So that API key is unique to you, which it's an extra step of authorization when you want to invoke your API Gateway. So associated with the key then is the workshop, the name, and the API, which is the REST API we created previously. In order to use your key, you need to use a usage plan, an API Gateway usage plan. Again, that's just some standard setup. This is your REST API, and the rest is names. API Gateway usage plan key. So this is where you associate your key with your usage plan. So again, this is our usage plan, and this is the key that we use. And we tell it the type of key that we're using, which in this case is an API key. So this is our resource for our property search API. And this is the resource for our property detail API, which gives us the property details. So for each one of those resources, we're going to have an associated method. So this is the update property method, API Gateway method, authorization type is none, HTTP method, API key required is true because we need an API key to allow us access. We're using post. The type is AWS, and we're showing that we want to invoke this Lambda function. So when we call this method, we want to invoke this Lambda function, which is Lambda function table update.arn. So that's the ARN of our update table Lambda function. Then we create our response types, what we want in the headers. So here we have for our headers content type, x.amz, date, authorization, API key, etc. The allowed method, so we're allowing post plus options, and access control allow origin. Here you probably want to further refine that to your domain name of your application. For us, we're going to use star as we're running from local. And then we create a response template. For us, we're not going to do that, but we're just going to return application JSON. We assign the resource ID, which is the update property resource we created previously, and the REST API we want to associate it with, which is the REST API we created previously also. And then we have the method responses. Again, we're just going to say that these responses aren't required. We set them to false, but for cars to work in our use case, we will need to return those headers from our Lambda function. So then we have an API options method. So when you run API gateway requests from a browser, you first have to send a pre-flight request, which does some checks for headers and etc. So we're going to have an options method, which is just a mock method for each one of our APIs. So it's pretty straightforward. It's just tasked with, so API gateway just returns what headers are acceptable, and then your request continues on to the post, which is the part that you're interested in. So again, we have HTTP method options this time. Status code, we're going to return 200. We have the same headers again, same methods, and the same allow origin as before. Same response template. Pass-through behavior is when no match, which we won't even need that. Request templates, so we're going to return the status code 200. And this time, instead of type AWS, we're going to it's type mock. Everything else is the same as before. We're just going to send our 200 back, and this is the headers that we can send. So that goes through the same for the other. There's no difference so this is the method for the get properties. It goes through the same logic. We're using type AWS proxy, which means we proxy to the Lambda function. So any request coming to API gateway that hits this method passes the complete request to our Lambda function. And in our Lambda function, then we parse the request and to understand what we want to do with it. Everything else is the same. We create an options for the pre-flight request. We set all the same parameters, and that goes the same through all of our Lambda functions. So I just skip to the bottom of those. That's the options for our last one. And then we come to Secrets Manager. I'm going to let Jeff go through the stuff that he's initiated here for Secrets Manager. It's quite interesting in how to interact with Redis using the auth that we've defined here. And I'll let Jeff talk you through it.
So in order to set up our Redis cluster and use role-based access control, we're first going to need credentials. That is a username and a password that our Lambda functions can use to access Redis. And so we're going to use Secrets Manager to store that information. So here you can see that we're setting up those credentials that we're going to use to access Redis. And we're doing so by defining a AWS Secrets Manager secrets, which we're calling the ElastiCache credential secrets. And what we're asking here is to generate the password, the secret string for the secret. So we're going to give it a template. So Secrets Manager stores secrets is basically like a binary safe string, but it has some functionality built in CloudFormation that you can create what is more or less like a JSON string that you can parse with whatever, in this case, our Lambda functions. So we're going to start by having a template with a username, and we've hard-coded the username here to workshop user. We're asking it to generate a string key of password, and then we're telling it to generate a password of length 30 to not include these characters. So if you want to do this for another system that had characters it couldn't use, you can say, hey, don't use these, and then we've given it a name to refer to later. So what this will do is tell Secrets Manager to create a secret, to give it that form to create the actual password, and then to store it all as a string, which is sort of this JSON object that we can then later decode in order to use for our Redis cluster. So in order to use role-based access control for ElastiCache for Redis, you have to set up a user, of course, first, and we're going to let that user depend on that secret that we created. Now, the way that it works in ElastiCache for Redis for role-based access control is that you have an access string that sort of masks what a user can do. So for simplicity, we're letting this user read or write any key in the Redis cluster. Of course, in production, you're probably going to want to limit this to something that's a little more restrictive. But we're going to then resolve the credentials that Secret Manager created with these resolve stanzas here. And so users in Redis can have more than one password, which is why this is a list. Of course, we're only going to have one right now. And we're telling it, hey, go to Secrets Manager and resolve the secret called cache cred secret. Pull the secret string from it, and then from that, parse it and extract the password. And we're going to do the same for the user name that we're going to assign to both the user ID and the username for our Redis user. So this is taking the credentials we made in Secrets Manager and it's creating a user in Redis for us. And then we're going to go ahead and create a user group. Users in ElastiCache for Redis have to be members of user groups to make them useful. So we're defining that user group. We're going to give it an ID that we're going to later use to refer to when we create the cluster itself. And then we're going to define which users are part of this group. It is a requirement of the ElastiCache for Redis system that you always have a username default as part of the user group, but this workshop user here that we've defined and created credentials for earlier is the one that our Lambda functions will actually use to access Redis. So then, of course, because our Redis cluster needs to operate in our VPC, we're going to have to define which subnet groups it's part of, and they just refer to the ones that Lee talked about earlier that we created. And now we get to the meat of creating our Redis cluster. You're going to notice that this is called a replication group in CloudFormation. That is because what it's doing is there is a way to deploy ElastiCache for Redis that is called cluster mode enabled. And rather than just have a number of nodes that have sort of a failover system set up among them, they have multiple sets of nodes that are shards where the data is sharded between them. And this is a more advanced way of deploying ElastiCache for Redis that's going to let you do some more interesting scaling options with respect to adding and removing shards on demand. It lets you create much bigger sets of cache memory. We don't need that for our example today, and so we're going to create a simple replication group, which is just a number of nodes that have an automatic failover system within them, but all of the data has to be able to fit within the memory of a single node. So we're defining that there as a replication group, and we're going to define some properties for our ElastiCache cluster. Of course, we're going to turn on at-rest encryption. We're going to say that we want that automatic failover enabled. So we're going to have a primary and some replicas. If our primary node fails, one of those replicas will promote itself to primary and take over the job of reading, servicing the reads and writes for the keys. Our cache node type. So ElastiCache for Redis is an instance-based service, which means that you have to choose your node types or really instance types in order to define how much memory they're going to have to store your data as an in-memory store. We picked an R6G large here. Of course, if you go up to an extra large, you'll get twice the amount of memory and so forth. And so the parameter group name that you'll see here is important because it also will define whether or not this replication group ends up getting deployed as cluster mode enabled. Setting it to the default Redis 6x says that I want it to be a replication group. There's another parameter group name that has cluster mode in it that will make it a cluster mode enabled group if you choose that instead. So here, of course, we're just telling it which subnets we want it to live in for that subnet group that we defined above. The engine is defined as Redis because ElastiCache also supports an engine called memcached that we're not using today. So engine version has to be 6.0 or higher because Redis 6 is when we started to support the ACL system that allows us to do that role-based access control that we're using today. Multi-AZ enabled lets us say, hey, we're going to deploy this across multiple subnets. Let's make sure we're deploying our nodes in multiple AZs for the highest level of availability. This simply defines that in addition to the primary that always has to be part of a replication group, I'm going to add 2 extra replicas for 3 nodes total for my replication group to give me that 3 AZ deployment. And then finally, we're going to make it part of that refer to itself security group in order to make sure that the Lambda functions that need to talk to our Redis cluster are able to do so. You must, by the way, if you want to use role-based access control, have TLS enabled transit encryption, right? Which you want to anyway as a best practice. And then finally, we're going to say these are the user group IDs. We're only going to have one. If you remember, we created that user's using the credentials for security manager. We put it into a user group. Well, now we're going to refer to the user group ID that user is a part of here. So when we create this replication group, it's going to automatically let that user read and write from the Redis cluster.
So I'm just going to walk you through the Lambda function, which is tasked with updating the DynamoDB table. We just take our normal imports. Botto3 is what we're using. So we create a resource, which is our DynamoDB table. And then we create a table resource, which is a Botto3 table type of DynamoDB. And we pass in the name, which we've saved in our Lambda function environment variable, which is here. We create that outside of the handler. So if you have frequent invocations, that this is only created once. So you're not creating a new resource every time your Lambda function is invoked, that your DynamoDB client is passed across invocations. Then we move into the handler. We created some dummy response. And then we start making our statement to update our items. We initiate our maps for holding our expression attribute names and our expression attribute values. Then we pull our keys from the event. So our event is what's coming from API Gateway, and the keys is the keys of our item. So event keys, primary key, event keys, and sort key. So we assign those both to variables. Then you'll see us have some heavy comments here to sort of highlight what's going on in the next step of code. So first we assign our expression attribute values, which is basically assigning a variable to each one of the values that's coming through. So in this case, we're going to say we have an agent, and this is the value of the agent. Again, we do the same thing with our expression attribute names. So basically what we're doing is we're assigning a variable name to the value. The reason we do it for this is because DynamoDB has a list of reserved words, which you can see a link for here. We don't want to clash with those reserved words, so we assign each of our keys to a variable name, which means that we won't even if the word does clash, it won't, because it's assigned to a variable. DynamoDB will be happy with that. And then the outcome of our expression is going to look like this. So it's going to be set your variable name equals your variable value, and then they'll be with a comment between each of them. So if we were to say another agent there, or agent C maybe, it would look like this on the output. So this is what this loop does. So we're taking for each key value pair in our data, which is sent from API Gateway, we loop through it and we assign those. So here we have expression attribute values, here we have expression attribute names, and then we assign both to our statement, and our statement's used as our update expression. So then we come in, once we have those maps, we come into our update item. So we assign the keys that we gathered before from the event. We call the update expression. We pass in our statement. This we call a -1 here, so we cut the trailing comma off the end. That's why that is -1. Expression attribute values, we pass in that map. Expression attribute names, we pass in that map. And then we build a response code. So we're just saying the status code is 200 because in this instance it was successful. We pass a message of success, and then we print some logs just so you can debug in CloudWatch. Again, then if we have an exception, we're going to say that the status code is 400 and that something went wrong. And then importantly, we pass back the headers. So as we previously mentioned, API Gateway, we use that to pass a response. So everything is passed to the Lambda function. So that ultimately means that your Lambda function is responsible with returning headers and everything else. So your headers here must exactly match what you've defined in your API Gateway, which we've done in CloudFormation. So you can see that the headers are all the same, that we've defined, our methods are the same, and that we've access control allow origin star. So you would want to further refine that. Then we return the response. So that's basically, there's not very much in here. That's how we update our items. If the item exists, we update it. If the item doesn't exist, then we add a new item. And that's how DynamoDB interprets the update item API. So now Jeff's going to go through the two Lambda functions which we use for Redis, and we'll see how they work.
So first, I'm going to take a look at the function that's responsible for populating our property cache. And so this is the one that's invoked from the trigger from the DynamoDB stream that has those events with changes, and it's going to take that information and put it into the Redis cache. So I'm importing the libraries that I'll need, Boto 3, of course, which is the AWS SDK for Python. You'll notice this interesting one here, which is type to serializer. So if you ever get a chance to go and look at the DynamoDB JSON that represents a DynamoDB item, it has multiple levels because the type of that item, whether it's a string or a number or whatever, is encoded in that. As you'll see in a minute, Redis will not accept that multiple level, and we're going to have to do something about that in order to make it types that we can store in Redis. So what we're going to need next is our environment variables in order to make sure that we're connecting to the things that we need. And so, of course, we're going to need to figure out what region we're in to connect to Boto. But next is going to be our cluster endpoint. So this is the endpoint we're going to use for our Lambda function to connect to our ElastiCache Redis cluster. These environment variables were populated, remember, when we defined this Lambda function in our CloudFormation template. So the next one we have is the ARN of the secrets manager secret that contains those user credentials to authenticate to ElastiCache for our user. So this is not the credentials. It's simply a resource identifier that lets us go to secrets manager and ask for the secret content to get the credentials. And then finally, we have the index key. This is whatever name that we've picked for the key that holds the geospatial index in Redis. So the next thing that we're going to do in our code is to go and make a connection to Secrets Manager, and we're going to ask Secrets Manager for the secret value for that ARN. This, remember, is more or less a binary safe string, so we're going to have to decode that string in order to get the bits of information that we want. We're going to call the Python JSON load s or load string function, which is going to take that string and make it a Python dictionary. And then we can go ahead and just get the username and password out of the dictionary that's created in order to connect to Redis and authenticate. Then we're going to actually make the connection to the Redis cluster using the Redis client. This is one of those dependencies that we talked about before that's going to have to be bundled in the zip file to deploy these Lambdas. And we're going to make a connection to our Redis cluster using the endpoint that we got from the environment variable. We're going to use the credentials that we got from Secrets Manager. We're going to make sure, of course, that we have SSL turned on. And then once our connection to the Redis cluster is made, we're going to be ready to go ahead and do some useful stuff. And then finally, I'm going to instantiate that deserializer I talked about before, which is going to let us turn that DynamoDB format into a Python one that we can use to insert data into Redis. As Lee noted before, all of the stuff that we've just talked about happens before the Lambda function is defined. And what that means is that the Lambda system itself can then sort of memoize or cache this. So it doesn't necessarily have to, go to Secrets Manager to get the secret info or make a new connection to Redis every time it invokes the Lambda function, which will hopefully save us some startup time. So in the main handler function, what we're going to do is we're triggered by the Dynamo stream and we're going to get handed this event. So this event will typically contain one or more records, and we're going to iterate then over each of these records. And we're going to take a look at that record structure and get something called the event name, which is the operation that happened within DynamoDB. Did I insert something new or did I update it? So if it was a put item, which is an insert, or an update item, which is a modify, we're going to have to look in that record for a field called new image, because that's the way that the new data that's inserted into Dynamo is emitted in the event. If it was a delete, which shows up as a remove operation, it's actually called old image in the event. We're going to need to pick that out instead. What did this look like before it was deleted? We need to know that because we're going to need the key in order to delete that key from the Redis cache to get rid of it so it doesn't live in the cache anymore if it's been removed from DynamoDB. So here's a bit of fanciness using a Python thing called a dictionary function that lets us say, I want to use that deserializer and I want to take all of my DynamoDB structure and I want to turn it into a Python dictionary instead. That's all this is doing there. And I end up with a dictionary called property details. So one of the things is that even though we've converted this to Python types now, it turns out that Redis has some limitations on what types that you can store in Redis as well. And one of the things that Redis doesn't allow is Boolean types. It doesn't have a Boolean type in its system. So that's not too hard to deal with. All we're going to do is we're going to iterate through all of the property details. And if we happen to see any Booleans, we're just going to convert them to strings because that's good enough for our system and what we need in order to store in Redis. If you were making this into more of a robust production system, you would probably want to go a step further. And instead of just having a for loop look for only Booleans, look at all of the possible types in Dynamo and how they're stored in Redis and make sure that you're doing the right casting and conversions in order to be able to store your data. So if you remember, we need a unique key to store these property details in Redis, and we decided to use the partition key and the sort key joined with a £, which is what we're doing right here to create that key. And then it comes time to actually, go ahead and update Redis itself. And so if it was an insert or a modification, we're going to call a Redis function that just says, hey, listen, I want you to take that detail key and I want you to make the value of that key all of the details for that property. Then we also want to go and we want to add the property to the geospatial index, right? So we want to say, okay, if we're adding a new property or we're updating it, we're going to call and say, I want you to, for that property key, add it to the geo index for this longitude and this latitude. And then Redis will add to that geo index all of that data. So then when our clients come and they do a geo search for a radius, we're going to get this key back if it's within the radius that they wanted. If it was a deletion from DynamoDB and it's a remove function, then we'll simply remove the key from Redis, which will then remove the associated values. And then we're going to remove it from Redis's geospatial index. You're going to notice this doesn't say geodel. The reason why is because under the hood, Redis implements geospatial indexes as a type that they call sorted sets. And they asked just to use the sorted set function instead of creating a whole new geodel one that points to it. And that's why this says zrem here, because that's the call that you make to remove something from a sorted set. So next I'll take a look at the Lambda function that gets invoked when we then want to go query the Redis cache. So all of this code up top that you're looking at is the same as what we just looked at for the property cache population. It's going to do the same, connecting the secrets manager and getting the credential values and then making a connection to Redis and authenticating with those credentials that we got. The only difference above the Lambda handler definition is that I have a constant that simply sets a default search radius here to make sure that we constrain the results, because if we were covering the entire country, we don't want to return an enormous number of results if our customer really only cares about a smaller radius. So when we look at the handler function definition, then when we want to query Redis to get information back, we're going to take a look at that request body that's coming in from the API gateway proxy, and we're going to use its path to decide whether the customer wants to do a geospatial search or to just fetch the data associated with a single property key. I do this by looking at the request path and seeing if it ends with the phrase search. And if it does, I know that I'm going to be provided a longitude and latitude for my geospatial search. I'm going to go ahead and say, let's see if the customer's provided a search radius. If they haven't, I'm going to use that default search radius from the constant I defined before. And then we're going to invoke a geospatial query in the Redis index to get the data back to figure out where all our matches are. One interesting thing that you'll notice here is that we're telling it that in addition to the Latin long that we're going to search and the radius that we also want Redis to return us both the coordinates of the matches and the distance from the center. And we want to do that because we want to display that data in our UI without having to round trip back again on a match and get that information from the key property details, right? We don't want to have to round trip for every match. And so getting those extra details is important to avoid those round trips from a geo search. Now, if instead the customer clicked on a dot and they wanted the detail for a property, that request path is going to end with detail. And then all we're going to do is just go ahead and get our property key and go to Redis and say, hey, give us the information. I have a bug here where this says search latitude and it should say property key. So in real time, we can see that. We'll fix that and get it updated in the repo. But we're going to get the results back. So the hgetAll is going to get us the information with the property key, and then we're going to return it back to the API. And that's going to be all the data that's displayed in the popover when you click on that property.
Okay, so I'm going to take you through the flow of the requests using the AWS Web Console. Here we are in API Gateway Console, and we're going to find the demo API, which we have here. So we're going to click on that. So what you will see from here is our resources in blue. So if you remember from the CloudFormation template, we had each of our resources. And then you also heard Jeff mention about taking the tail of the path in his Lambda functions. This one is the tail is detail, and this one is the tail is search. So he knows which one of those APIs is being hit based on the tail of it. So we're going to go through maybe a sample workflow where we update a property. So we can go ahead here and we can click on post. It'll give us more details. So here you can see the information on the method request. We can click in there. We can see that we have an API key required. Yes, everything else is left in default. Integration request. This is just going to show that we're using a Lambda function in the back end and that we pass everything through to that Lambda function. Everything else is left as default. So if we go ahead and test that, here you'll see you can pass in query strings, you can pass in optional headers. We're going to go ahead down here to the request body, and we're going to pass in a request body. What I'm going to pass in there is a sample property. So we're going to go ahead and use the request body here, and I'm going to pass in a sample property. So here you see the property. We pass in some keys, the PK, the S key, and then the data. So the data is just going to be the address, agency, agent ID, etc. And we're going to go ahead and press test. So here you'll see the response coming back from our Lambda function. So we're getting 200 and it's successful. So we're going to go on ahead over to the Lambda function just to see that the logs for that. So if you click here, that'll take you over to your Lambda function, which is brought up here. You can see our Lambda function that we walked through earlier. We can click on monitor, and then we click on view logs in CloudWatch. So that'll bring us over to CloudWatch, which we have here. So you'll see here we have any of the updates that were made already. So we click into one of these log streams. And then if we use view as text, it'll expand this for us. So we can see in our log that we successfully persisted item, and that is the one that we shared through API Gateway. So now what we're going to do is we're going to go back to API Gateway, and we're going to do a search. So we're going to do a property search, which returns a list of all the properties that match our radius. So as with before, everything's got the same setup. It's got a different Lambda function here on the right-hand side, which is Lambda Function cache query. We'll go into test again. Again, we'll skip down to request body, and we'll pass in the necessary parameters, which is the latitude, the longitude, and the radius that we need. So we'll go ahead and hit test. And as you see, we've got a list of keys plus the lat long. So this is the key for the item. And then we have the latitude and longitude for each one of those items. And we use that then to highlight our points on our map. Again, we can go through the Lambda function for that. So we go back to Lambda functions. We go demo, and it's the cache query, and we'll just pull up the logs for those. So go to monitor, and view logs in CloudWatch. So here we have our logs. We can click into that, see the complete log. And you can see the logs that we have some verbose logging in our Lambda function. So we see that we retrieved our keys from secrets, successfully got the secret. Now we're connecting to our Redis cluster, successfully connected, and then we successfully return a 200 response with our list of keys. So then that leaves us with one other Lambda function, or one other API, which is get the details for a property. So again, we'll go to post and we'll do a test there. Once again, we'll scroll down to the request body. We'll pass in a sample key. So this time property key, and we pass in the sample key. Again, we run test. As you can see, that gives us back everything for that item, for that property. We can run through the logs for that again. So we go back to our Lambda functions. And we go to our Lambda function logs, which is here. And we click on the most recent. Again, we'll view it as text. And the same again, we can see that we just connect the secret managers, we get the key, we go to the Redis cluster, and we get the item back with the key that we've passed in. And that's basically how you test your APIs using the API Gateway console, your Lambda function console, and the logs that you expose in Amazon CloudWatch.
So now we'd like to take some questions that we've gotten from the chat in order to maybe give you some depth and help explain a little bit more how we've put this together.